All right, so what I want to do is I'm going to write each of these things in isotropic notation and determine the number of neutrons. The first thing I want to do is figure out, well, what's the format of what I need to write down. And I'm going to write things down looking kind of like this, where you have X as the element symbol, A is the atomic mass number, and Z is the atomic number. The atomic number is actually the number of protons, because it's the number of protons that really defines what an element is. If I have a different number of protons, really I have a different element altogether. I can change the number of neutrons in the element, and what that would do is that would make different variations of that same element. It's just what you're doing is you're making a heavier version or a lighter version, whatnot. So what you would do is you would change the number of neutrons, and that would change what we call the mass of the element. And you're creating what we call an isotope. If you change the number of electrons, that's a different story, and that's where we create an ion. But if you change the number of protons, that is an inherent property of an element. And if I say I add an extra electron, or an extra proton, what I'm doing is I'm not messing with that same element. I'm just moving myself over to a totally different element altogether. So the first one is sodium, and they gave us the atomic mass that they want us to write down. So let's see. If I want to write down sodium, first thing I got to do is find it in the periodic table, and I put my periodic table up here. Sodium is Na, and Na has 11 protons. So my symbol would be Na, and I know that this number is 11, and that number down there doesn't change. If it's a 12, you're no longer dealing with Na, you are dealing with magnesium. Got it? All right. And then obviously they want you to have a 24 up here. Now, if this is a neutral element, then the question that you might have is, well, how many electrons does it have? Well, if it has 11 protons, then it has 11 electrons to balance out. Those negative electrons will need to balance out with the 11 positive protons. Now, I guess the next question you would want to ask is, okay, well, how many neutrons does this have? Okay, well, let me write this down. As far as protons go, I'm dealing with 11. And then as far as neutrons go, I know that if I add the number of protons to the number of neutrons, I'm going to get this number 24. So let's say P plus N is equal to A. So if I want to figure out what A is, I just subtract P from both sides, and so I have N is equal to A minus P. Don't memorize that equation. It's not really an equation that you need to memorize, but rather it's just kind of showing you what I'm doing here. I have 24 minus 11, and that's equal to 13. And then you said, then I guess another question you might have. All right, so first of all, the answer to this problem is sodium. The isotropic notation of it looks like this, and that is for the sodium isotope with the atomic mass of 24, and the number of neutrons that it has is 13. Now, one question you might have is, if this is the atomic mass up here, 24, and that accounts for all the protons and all the neutrons, what about the electrons? There's 11 electrons that are tied to this. Doesn't that add mass as well? Wouldn't this 24 be something more like, I don't know, 35, if I'm considering, the 11 extra electrons? And I suppose my question to you would be like this. If you were standing on a scale, okay, and you were really concerned about your weight, and you wanted to make sure that you didn't weigh a certain amount, okay, and so you stand on a scale and you said, oh man, I'm so heavy. And I said, okay, well, what you need to do is you have an eyelash that is stuck on your forehead. You need to take that eyelash off and then stand on the scale, and it will make you feel better because you'll be lighter. And the answer is, of course you'll be lighter. Technically you will be lighter, just not enough to really count for anything. And the scale that you have, I mean, unless you have a pretty incredibly accurate scale that is mind-bogglingly expensive, then if it's a bathroom scale, it's not going to read anything different if you take the eyelash off of your forehead or not. It really doesn't make much of a difference. Well, that's what an electron is. An electron it's like way smaller than a proton. If a proton was like 1 atomic mass unit, and that's actually what it is. Actually, I'll tell you how big it is. It's 1.0073 atomic mass units. An electron would be 0.00055 units. So it would be like I'm accounting for all of the protons, and I should account for all the neutrons because a neutron weighs 1.0087 units. But I don't need to count for any of the electrons because adding 11 electrons to this number doesn't really change much. But you see how the protons and the neutrons just are about the same size. The neutron is a little bit more massive than the proton. But if I add on an extra, 11 extra electrons, it's not really going to change my number of 24 because I have, like, let's say I want to multiply this by 11, I want to multiply this by 13, and I want to multiply this by 11, and then I'm going to add them all up. The answer I'm going to get is 24.0, maybe a 1, blah, blah, blah. But I would only really care about these maybe 3 numbers over here. Or actually in this case, I'm only caring about the first 2 numbers. And so adding those extra electrons isn't going to change this 24 one bit. Does that make sense? I hope it does. All right, on to the next one. Hydrogen with a atomic mass unit of 2. We call that deuterium. And so the hydrogen, that has an H. And the number of electrons that we're dealing with, actually, I'm sorry, the number of protons that we're dealing with is 1. And there's a 2 up here. And so that tells me, okay, well, that gives me protons is equal to 1. Electrons should be equal to 1. And my neutrons is equal to 1. Because it's the protons plus the neutrons should give me 2. And that's that. All right, lead. So lead. Lead, let's see where it's at. Lead is right over here, 82. So I know that lead has 82 protons, and it's labeled PB. And what does that PB stand for? Well, it's the old school name of plumbum. But anyway, there's an 82 down here, and there's a 208 on top. That is the isotropic notation. And as far as how many neutrons I'm dealing with, well, I know that my protons is going to be 82. I know that my electrons are probably going to be 82, assuming I'm not dealing with some kind of isotope, or I'm sorry, ion. And then my neutrons is going to be 208 minus 82, which if I did that calculation, I'm going to get 126. And the final one is uranium. Uranium has a Z of 92, and its number is U. Or I'm sorry, its symbol is U. Let me just double check that. 92 is down here. There we go, uranium. See, told you. Got this stuff down. All right. And the number they want us to put up on top is 235. And as far as breaking this thing down, as the protons, there's 92. If there were 93, you're not dealing with uranium anymore. You would be dealing with, what is that? Nope. Nipium? Nipininium? I don't know. I couldn't read that because my my periodic table isn't very clear over there. All right. So the protons is 92. The electrons is also 92. And the neutrons would be 235 minus 92, giving me 143 neutrons. And that's how you do it. It's pretty straightforward.